In this section, we're going to talk about networking communication between your services. Networking communication, in my experience, is a lot more complicated than what people think it is. There's a lot of nuance here, and there's a lot of timing and race conditions that can adversely affect communication here. And we're going to take a look at a lot of those things during this section so that you have a really good mindset about how to be thinking about this and coding it up. It also requires that when you are architecting your system that you code things with retries and so on to be fault tolerant. So let's start by talking about the 8 fallacies of distributed computing. This is actually a pretty well-known thing, and I put a link here to a website where you can go and read a large document that goes through these. But this, I put it here as the first slide in this section because it really drives a lot of the conversation. So let's walk through some of these fallacies of distributed computing. The first fallacy is a lot of people think the network is reliable. But in reality, the network is not reliable. The network connections, they come and go, there's timing issues with it, and so on. And so what this means to you is that when you are architecting your distributed cloud application, your application needs to be able to handle error handling from network communications, and typically we do this by performing retry operations. So we tried to make a connection, that failed for some reason, we're going to retry and make the connection again. The next fallacy is that the network latency is 0. People think that, well, the 2 machines are next to each other and there's a wire there, and the communication is going to go blazingly fast. However, as I mentioned earlier in this course, a lot of times for resiliency reasons, you want to put different services on different VMs, possibly in different racks, possibly in different availability zones, possibly in different regions even. And the topology, or where these things are located, you really would like to not have to think about that. You want the orchestrator to decide where these things go and to do the right thing for you. What this really means is that latency is not going to be 0. There is going to be some performance impact or time required for your client to go and talk to a server. So this means you should try to minimize the number of requests that you are making from your application. You don't want to make a very chatty application that talks a lot. You want to reduce those number of requests as much as possible. The next fallacy is that the bandwidth is infinite. No matter how many bytes you send, it's going to be able to take it all. But that's not true. A lot of services, they do throttling. They will only accept from a single client. Well, let me rephrase it. A lot of services are multi-tenant services. So there's a lot of different clients who are using the same service. Well, if one client is hammering that service with requests, then that service might not be able to handle requests from other clients. So what's frequently done is the multi-tenant service implement some kind of throttling mechanism, where if a certain client is sending in, more than 1,000 requests per second, it starts immediately failing those requests and saying the server is busy. The server may not actually be busy. It's just going to report that it's busy because it's trying to leave some bandwidth available for other clients that may be trying to hit the same service. And while you're communicating between services on a wire, there are other services that are communicating on that same wire. So some of those services might be sending a lot of packets on that wire, and so your service might be having trouble getting some packets in. So again, the bandwidth is not infinite, and in fact, not only is it not infinite, but it dramatically changes over the lifetime of communication. The end result of this is that your application should send small packets, small payloads, right? Try to send small pieces of data, not large pieces of data whenever possible. The fourth fallacy is that the network is secure. The application has to secure its data and authenticate requests, is what that means to you. Now, I have talked about how when you create a cluster, a virtual network is set up between all the nodes of the cluster. And that is true typically, and therefore no other services or machines outside that cluster can see any of that traffic. So in that regard, the network is secure. But let's say inside that cluster, somebody goes and loads some third-party component, right? Some component that you got from a customer maybe, and you're going to execute some of its code. You don't know what that code does anymore. And that code might try to talk to other services that are within that cluster, and maybe it shouldn't be allowed to. And maybe it's looking at some of that traffic. So you have to think about those kinds of things carefully and possibly set up security boundaries around them where every client request coming into a service, even if it's on the same cluster, you may want to do some kind of authentication there to make sure that it's allowed to do what it's trying to do. This is especially important if you run third-party or untrusted code inside your cluster with you. The next fallacy is that topology doesn't change. So again, I've mentioned where the orchestrator might decide to take you have two different services and they happen to be on two different VMs on the same physical machine, and then the orchestrator decides for some reason, maybe for load balancing, to take one of those VMs and move it somewhere else. The orchestrator is allowed to do that because, again, that's considered an implementation detail, and it's really something that you're paying the orchestrator to do for you, to do this load balancing so you get better performance. And there may be other reasons why the orchestrator does it as well, possibly failure, or just some other reasons. So in other words, the topology, where your services run within a cluster, that can change over time dynamically, really behind your back. So just be aware that what this means is that any latency, bandwidth, or endpoints, a good one is endpoints. If you know the IP address and port of a service, the orchestrator might move that service somewhere else, and now the IP address may no longer be accurate anymore. So you have to write your code, again, resilient enough to be able to handle these kinds of performance differences or endpoint differences. I will talk more about the endpoint stuff very shortly. Another fallacy is that there is one administrator, meaning that there's only one person who's control. But really, in an orchestrator world, you kind of have this other administrator, which is the orchestrator, that's kind of acting on your behalf. And then, of course, you could have multiple people who are trying to configure the orchestrator. So this really means that changes affect the ability to reach the destination, right? You might think that there's a service, and I know its IP address, and I know its port, but maybe some administrator came in and made some change somewhere, and now that is no longer true. And you would like to be resilient against that kind of thing. The seventh fallacy is that the transport cost is zero. Sometimes you're charged for data that leaves a data center. In fact, frequently you are charged for that. So it's not just that there's the performance cost of it, but sometimes there's an actual, money, currency that's associated with that. And so when you are designing a service that's moving a bunch of traffic, especially if that traffic leaves a particular data center, a lot of times you're charged for that. So you have to think about the budgeting of the cost of running the service in order to handle that. And then the eighth and last fallacy is the network is homogeneous. And this affects reliability, latency, and bandwidth. In other words, it may not be all the same networking hardware. All the networking cards may not be the same speed. Some of it might be fiber optic. Some of it might be copper. Don't make any assumptions, right? All of this boils down to don't make any assumptions about the network. And in order to not do that, you're going to have to write code in a different way in order to be resilient against these kinds of fallacies of distributed computing. In this section, we'll talk about service endpoints. If you think about the original design of the TCP/IP world, you had an IP and a port. And what that mapped to was a PC, so the IP address represented some PC that was accessible on the network, and the port mapped to some service that happened to be running on that PC. And this was designed to allow a client to talk to a specific service on a specific PC. And on one IP, you can't have two or more services that are listening on the same port at the same time, right? This was a limitation that was built into that. Otherwise, there'd be ambiguity. If you had two services listening on the same port, when a client request came in, we wouldn't know which service to send the request to, right? The machine wouldn't know. However, that made sense many years ago, but today, we have one PC, and that PC can be hosting lots of different virtual machines. And one virtual machine can be hosting lots of containers. And each container can run its own service, and they all may desire to run on the same port. So now we have this kind of multiplexing issue where a client request comes into the PC, but it's really for a specific VM, for a specific container in the VM, for a specific service running within the container on the VM on the PC. And somehow we have to sort all this out. And we want to allow multiple, let's say, web servers listing on port 80, each running in different containers or on different VMs to be hosted on a single machine. So the original networking stacks weren't really designed to handle this. And so what has come up over time are various virtualization techniques to virtualize these IP addresses and ports. And as I say on the slide here, some people refer to these virtualization techniques as really hacks, right? It wasn't really designed for this originally, but now we're trying to make networking work this way, even though it wasn't designed to. So a lot of these virtualization techniques or hacks are things like the introduction of routing tables. We have source network address translation. We have destination network address translation. We have modifications to client code where you actually have to modify your source code to look for a different IP or look for a different port to go and talk to it because it could be on lots of different ports on the server machine. Really, this has all become very complicated with different technologies that work in slightly different ways. Some require modifications to source code, some just require modifications to infrastructure. When something doesn't go right, it's very hard to debug it and diagnose it to find out what went wrong. It's caused a lot of problems for people over the years. We really need something better. However, we have too much legacy stuff around, so it's very hard to innovate in this space and come up with something better. You know, network cards have been around for a long time and they work the way they do. Routers and switches have been around for a long time, they work the way they do. Same is true with the domain name service protocol, DNS, other protocols as well, etc. And so for the foreseeable future, the hacks are just going to continue and more virtualization techniques to try to make this better are going to come along. We just have to learn to live in this world because it just is the way that it is. I have this note at the bottom, beware, that service addressing and discovery, that is finding the address of a service within your cluster and discovering that and then talking to it, is really a lot more complicated than what people think it is. And we're going to go into some of those issues very shortly. Before we get into that, let's talk a little bit more about service scalability and high availability. Right? These are the two, holy grails of distributed cloud applications. Right? We want them to dynamically scale, and we want them to be highly available. To make things worse, as far as the service endpoint discovery goes and communication, we now run multiple service instances of a single service. So if one service instance goes down, we have other service instances remaining to handle that failure until the orchestrator goes and heals the thing that's broken. Right? And we do this, of course, for service failure and recovery, and we also run multiple instances so that we can dynamically scale up to handle a large client load or scale down in order to save money when we don't have a large client load coming in. Well, this means, since we're running multiple instances now of any given service, that the instance endpoints, they dynamically change over the service's lifetime. We scale up and new IP addresses show up. We scale down and those IP addresses go away. Or the orchestrator moves our service around from one node to another and the IP address goes and changes. Right? An instance fails and comes back up. The IP address is temporarily not working, but then it comes back up and it's back to functioning again. Right? So these are the things that's just dynamically changing all the time. Failure is always inevitable, so we have to embrace that this just happens. And then we have to code for it so that we can handle it in a robust way. Ideally, these IP addresses and possibly ports changing all the time, we would like to abstract this away from client code so that we don't have to write a lot of code to do this, right? We would like it to just kind of work for us as best as possible so the software developer has an easier time with it. So there's several ways to go about doing this sort of thing, and one of them is that each client wants to have a single stable endpoint for the face of the dynamically changing service instances endpoints. And typically, this is accomplished using a technology that is known as a reverse proxy. Now, the nice thing about the reverse proxy is it puts this abstraction layer inside your cluster, which is nice for the client application code and also for the server code. That's the good news about it. But there is a downside to it. And the downside is that every network request now goes through the reverse proxy. And this causes an extra network hop. Right, so that's the trade-off, right? You're having a simpler programming model where you don't have to deal in your code with the failure as much. And the downside is the reverse proxy is dealing with that for you, but it's introducing an extra network hop into your communication, which can hurt performance a little bit. So we are losing some performance in order to gain a lot of simplification. And many developers find this trade-off to be very desirable, so they accept it into their life. So in this case, the client is using some kind of domain name service, DNS service, that has to be at a well-known static endpoint in order to get the reverse proxy's endpoint. And then the DNS endpoints are usually cached in the client, and then they are re-resolved infrequently. But it's possible the reverse proxy could move around too. And if it does, you would have to re-resolve its endpoint in order to talk to the new location of the reverse proxy. And there's many examples of reverse proxies that I'm sure many of you are familiar with, such as a web server. A web server is a kind of reverse proxy, like Nginx or Microsoft's Internet Information Server are examples of that. If you use a load balancer, and I've used load balancers at a few places in my slides throughout this course, a load balancer is another example of a reverse proxy. And then API gateways, if you use any of those are another examples of reverse proxies. So on the next slide, I'll talk about reverse proxies, and I will also introduce the concept of a forward proxy, and I'll give you some ideas of what these things are used for. On this slide, I show infrastructure, client-side infrastructure and server-side infrastructure that uses proxies. Now, I was just talking about a reverse proxy, which is really on the server infrastructure side of things. That is, when you are creating a server, you could have your instance 1 and instance 2 of your service listening, and those would be on different IP addresses and ports, most likely. Maybe the same port, but different IP addresses. And then you put a reverse proxy in front of them. Now, this reverse proxy, it processes incoming requests into these servers. And reverse proxies, they can do a myriad of features or offer a myriad of features and operations that are available to you. And I list just really some of them here on this slide. The one that I was just talking about on the previous slide was that a reverse proxy offers a stable client endpoint over the changing server instances endpoints over here. As new service instances come and go for scale up and scale down, or as nodes fail and you get healed, right? The reverse proxy is offering a stable endpoint over here, and it's keeping track of everything that happens on the right-hand side. You can also use reverse proxies for load balancing, and there's level 4 load balancers as well as level 7 load balancers. Level 4 load balancers, they are load balancers that can handle UDP and TCP traffic. And it's level 4 because of the OSI networking model. They handle traffic that's happening at the level 4 level of the OSI networking model. So that means any UDP or TCP requests that come into a level 4 load balancer, those UDP and TCP requests can then be sent to any of the instances over here. But you can also use a reverse proxy for a level 7 load balancer. That's level 7 in the OSI model, which is the application layer. And that's typically used for HTTP or HTTPS traffic. With a level 7 load balancer, it can actually look at HTTP. So it looks at URIs. It can possibly look at headers that are in an HTTP request. And based on the information that it sees there, because it's richer, higher level information, it can use that to figure out how to go and direct traffic on the right-hand side. So maybe all incoming traffic with a certain header set to 1 comes over here, and traffic coming in with a certain header set to 2 goes over to here, for example. The reverse proxy, another kind of load balancing it can do is server selection or A/B testing. You might have version 1 and version 2 of servers here, and you could say to the reverse proxy, I want 10% of the traffic to go to version 2. I want 90% of the traffic to go to version 1. So you could do this kind of A/B testing, and 10% of your customers get to experience the new version of your service before you switch everybody over. We will talk about versioning and this scenario in more detail a little bit later in the course. You can also use reverse proxies for SSL termination, where you have a certificate over here and HTTP requests come into the reverse proxy. And now once that's done, you can make all the internal network traffic be non-encrypted. Just use HTTP instead of HTTPS. So it's only encrypted up to the proxy, and on the right-hand side of that, it's all unencrypted. You can use reverse proxies to do caching. So the first client request that comes in, it goes out to a server, the server sends some result, and then the reverse proxy can cache that. So any future requests that come in for the same data, the reverse proxy can just return it. It doesn't have to forward it on to a back-end service, and that can reduce load on your back-end services, allowing you to save more money because you don't need as many machines running if there's certain cached information that gets queried for frequently by a lot of different clients. You can use reverse proxies to do authentication and validation. Clients make requests into here. Maybe in their HTTP header they have an authorization information or some cookie information. The reverse proxy can do the authentication there. And so once anything reaches beyond that reverse proxy, we know that the authentication has happened successfully. And we know that this is a valid operation to be performed. The reverse proxy can be used to do tenant throttling and billing. Client requests that come in, the reverse proxy can say, well, I'm seeing more than 1,000 requests per second from this particular client. And we're just going to return failure here and not allow them to make that many requests into us per second. So we won't send any more traffic to the back end, so it doesn't have to deal with that kind of throttling, bookkeeping, or accounting. And I mentioned billing here as well. Some services bill for every request that comes into it. So if the reverse proxy does the authentication properly, it knows who to increment the billing counter for, right? Whoever they authenticated. So at the end of the month, they can go and send that tenant a bill. And then some reverse proxies use distributed denial of service mitigation. So if they see a lot of requests coming in over here, they can also do things to kind of stop accepting requests from those clients for maybe the next hour or the next day kind of thing, so that your service backends over here don't have to worry as much about distributed denial of service attacks that might be being attempted against your service. Now that's what the reverse proxy does. For completeness sake, I also put on the slide here the client infrastructure, and the client infrastructure can have a forward proxy, or as it's more commonly referred to as just a proxy. But when people say proxy, they typically mean a forwarding proxy as opposed to a reverse proxy. So this would be on the client infrastructure. It could be that you work at a big company and there's lots of computers within that company. Those computers are all making requests, let's say, to the same website to go get some information. So that company might set up a proxy itself, and so all the employees at that company, they make requests to this forwarding proxy, which can do a bunch of things before it forwards the request onto the server where it would hit the reverse proxy. So let's just look at some of the things that a forward proxy can do. Well, it processes outgoing requests as opposed to the reverse proxy, which process incoming requests. And the forward proxy, it can do content filtering. It might be that at your company, your administrators has set up the forward proxy to prevent certain traffic from coming in. There might be certain websites that your company has deemed to be inappropriate or not to be used, and so they can set up this proxy to say, well, somebody's making a request to this website, we're just going to shut that down right here, and that avoids any network traffic going out over the internet to hit there. That can be done for censoring purposes, or it could be done for translation. Maybe the employees here hit some website and it's some foreign language, and the forward proxy can translate the contents of that website into their language of choice, their native language, before the HTML pages are returned back to over here. Forward proxies can be used for caching. So if a lot of employees at the company are getting the same information over and over and over again, the forward proxy can go and make a request, cache it over here, and then simply return it. This way the requests don't have to go out over the internet. That saves the company money by reducing its bandwidth usage, but it also gives the employees a better experience because you're not hitting the internet. The performance is faster of returning that information back. The company might set up the forwarding proxy to do logging or monitoring. Maybe it just wants to know when people are in the office, or what websites are being used frequently, or how much data people are downloading. All this can be done for logging and monitoring, and it can be used to better fine-tune the client infrastructure within that company's and its offices. Maybe it needs more Wi-Fi routers. Maybe it needs more wired routers. And it can monitor this to see what would give the employees a better experience. And then forward proxies are also used frequently for client anonymization. If you make a request to a server, a lot of times your network, the client-side network information is sent to the server so it can go and send a reply back to you. But that might be divulging too much information to the servers, like possibly your GPS location information, for example. So people use proxies in order to do some kind of anonymization before the request goes out so that the servers know less information about the clients. And you can feel a little bit more secure in your identity or your location or other interesting artifacts about yourself. In this section, I'm going to take a lot of the things that we've been talking about, and I'm going to put them all together now so you can see it as a cohesive story. Specifically, we're going to be talking about a cluster. Within the cluster, we have a domain name service, and we're also going to have some reverse proxies in here too in order to allow the service-to-service communication to go. So first, let's say from the internet, a client request comes into the data center where the first thing it hits is a load balancer, which, if you'll recall, is actually an example of a reverse proxy. In this case, I have 3 instances of the website service running. So they each have their own IP address or port, some running on some VMs that are part of this cluster. The load balancer is going to choose one of those instances and send the traffic to it. Let's just say in this case it chose website number 1. Now, website number 1 wants to go and talk to the inventory service. But there's 3 instances of the inventory service. So it needs to know the address of the inventory service, and then it needs to go and talk to one of those. So if this is the first time we're talking to the inventory service, the website is probably going to talk to a domain name service that's also running within the cluster. And the domain name service really has a map or table in it that maps the inventory service. This is the endpoint of the reverse proxy for the inventory service. And for the order service, this is the endpoint of the reverse proxy for the order service, which are these red guys over here that I show inside the cluster. Now, after this website hits the DNS service and it gets the endpoint for the inventory reverse proxy, the website then will go and talk to the reverse proxy service. And it's really kind of a load balancer in this case that's then going to pick one of the instances of the inventory service and direct that request to it. In this case, I have it going to inventory service number 3. So now number 3 goes and does its work, and then it would return back. But I also have a note up here too, and it's a warning note, right? Because you have to remember failure is possible at any time. So while we're talking to inventory service number 3, it could go down. It could have received the request, and then it could have had an unhandled exception. So now the reverse proxy would know, because the orchestrator would tell it, and then any new requests that come into the reverse proxy, the orchestrator, well, it would send it to instance number 1 or instance 2 until instance number 3 is healed and comes back online. So the point I'm trying to make here is that it's impossible to keep endpoints in sync as service instances come and go. It's literally impossible, which is why I put it in bold italics letter. Your client could go and request the endpoint of something, and once you have that endpoint, when you go and talk to it, it may not be there anymore. And things will change, but things are changing dynamically, and it's impossible to keep everything in sync. So client code must be robust against this, and typically that's done with retries. Now, in this example here, if inventory number 3 goes down, it's possible that the reverse proxy could do the retry and make the request to inventory number 2 or number 1. So now the website number 1 isn't doing the retry because the reverse proxy is doing it on your behalf. Right? And that's a nice feature of reverse proxies, to kind of give you that abstraction or isolation so that you don't have to write the code. Whoever wrote this code for the reverse proxy has to deal with these issues, and you not so much. However, you're probably going to end up having to do retry code anyway for other reasons. For example, a timeout might occur. So you might make a request to the reverse proxy for inventory, and maybe it's just taking longer to respond than you thought. And so you might get a timeout inside your instance, and then you might want to retry because maybe the next time you retry it'll be faster. So you're probably still going to want some retry code, but the reverse proxy can maybe improve the performance because it's only one network hop instead of two. Another thing to be aware of, since failure is always possible, is that while your instance here is talking to the reverse proxy, which is in turn talking to an inventory instance, your instance could go down. Maybe this gets scaled down, or maybe you crash over here. So when inventory 3 returns a result, it's trying to return back to your instance, but your instance went down and is no longer running. Well, in that case, the client all the way back here is going to get the failure because you went down when handling their client request. And so they will actually have to retry from back here to make a request to the load balancer. The load balancer should send it to any instance that's up, and then the whole process will have to start all over again. So the point of all of this is to say that the networking is challenging, and that retry support in these various mechanisms is mandatory. It's really not something that you can just say, well, it works 99% of the time or better, and so I'm just not going to do it at all, right? You really want to be resilient to these kinds of failures. You really want to make sure that you have retries in all the various steps of the way. Another thing that I should point out on this slide is that this reverse proxy, the way it looks like right now, is it is a single point of failure. And that's actually true of the DNS server too. If this goes down when any of the websites are trying to query the DNS, if it's down, then certainly it can't talk to any of the other instances. Or if the reverse proxy goes down, then you can't talk to any of the instances. So you want to design the DNS and the reverse proxy to be resilient and not be a single point of failure. For the same reason we have 3 instances of the website, 3 instances of the inventory, 2 instances of the orders, right? Is so that there is no single point of failure. I've said a number of times that the orchestrator is responsible for reconfiguring the load balancer whenever a service instance comes or goes. On this slide, we're going to take a closer look at that and see how that actually works. What I show on this slide are internet requests coming in, and then they're hitting a load balancer, which is a type of reverse proxy. And the load balancer has inside of it a table of the IP addresses and ports of the various services that are running on the different virtual machines elsewhere inside the cluster. And then on the right-hand side, I have a VM that's running the first instance of the inventory service, and it's listening on port on an HTTP port, let's say. And I have another instance running on a different VM, and I have a third instance running on yet a third VM. Now, when you create a load balancer, you typically can configure it with a bunch of what's called load balancer service probes. And here I show an example of what 2 probes look like, but you can actually have many probes that are associated with a single load balancer. With each probe, you specify some amount of time, like 15 seconds. And you're saying to the load balancer, every 15 seconds, I want you to go and probe each of these service instances to see if it is healthy or not. And then you can say, probe it on port 80, and then I have another one that we're going to probe on port 8080. And then I can say, and what is the path? So this would be something like causing the load balancer to make an HTTP request to IP address for inventory number 1, port 80 / healthprobe.aspx, or whatever you want over here. And the load balancer will send this probe out to these 3 different virtual machines, all the ones that it knows about. And it will do it every 15 seconds. Now I have 2 rules here. So the load balancer is actually going to probe both ports, 80 and 8080, every 15 seconds across all of these. Because you can have multiple services listening on each of these, but of course each one would have to be at a different port. Okay, so now let's say the load balancer goes and sends a probe out to all those machines, and they all returned back an HTTP 200 initially. So that says to the load balancer that all of these machines are saying it's okay, right? HTTP 200 means okay. And so the load balancer says they're all doing fine. So any request that comes in from the internet, I can send it to machine 1 or machine 2 or machine number 3. Now let's say that machine number 1, something has gone wrong. So the next time the load balancer probes all these machines, machine number 1 returns a 503 back. Because it's not returning back 200, really anything other than 200 indicates failure, the load balancer says, okay, machine number 1 has not returned a 200, so there's something wrong with it. So any future network requests that come in, I will not send it to machine number 1. I will send it either to machine number 2 or machine number 3. Now let's say that machine 1 heals itself, and so the next time the load balancer sends a probe, 15 seconds later, it now returns a 200. Then the load balancer sets this back to green, indicating that any new requests that come in from the internet can now once again be sent to any of the 3 machines that are on the right-hand side. One of these machines might go down completely. Maybe the service stops running, or maybe the network controller goes bad. Or maybe the kernel crashes on Windows, you get a blue screen in that case. So if the load balancer sends out another probe and this machine number 2 gives no reply back at all, then the load balancer sets this to red to indicate that there's something wrong with machine number 2. So now any client requests that come in from the internet will either be sent to machine 1 or be sent to machine 3. All right, so now that we've been talking a lot about networking, let's now focus on what's really necessary in order to turn a monolithic service into a microservice. So instead of having all the code residing in one place, we're now splitting it up into different services, and we're going to introduce network communication in order to talk between them. What I show on this slide is what you would typically have today. In your monolithic service, somewhere in the code, you're going to call some method, and then you're going to pass in some arguments, and this method is going to return some result back out, right? Pretend this is whatever programming language you want it to be. Well, what we're going to do now is we're going to turn this method call into a network call. And a lot of times people think, well, that's all we got to do is turn the method call into a network call. There's a lot behind that, and it turns out to not be as simple as a lot of people think. So let's go and really look at this in depth. Well, in order to do that, you're going to have to turn this method really into a web service now. And remember, you want your web services to be in different programming languages, potentially, right? We want to maybe use Node on the client and .NET or Java on the server. So now you're going to talk over a network protocol. So now you need to define an explicit language agnostic, that is programming language agnostic, multi-version API contract now. And I think you should be very explicit about that. This is a formal contract that you are writing, and it's going to last you years and years and years into the future because different services version over time. So you really want to spend a lot of time on this and really think it through and come up with a good contract. And I'll say more about these contracts as we continue this talk. When you go and make a contract like this, it's going to be over the network, you're going to lose certain language features, depending on which language you're using. And so you tend to lose things like IntelliSense support. You tend to lose things like refactoring, right? If I rename this method and I want to rename all calls to this method, you can't do that easily anymore, right? And a big thing that you lose is compile time type safety. I'm a huge fan of compile time type safety. I like it when the compiler tells me something's wrong rather than me finding out that something's wrong at runtime, especially if runtime in production. So you're going to lose a lot of compile time safety. Now you can get some of this back by creating client libraries, but that's additional work that has to be done, and you have to keep the client libraries that are for a specific programming language in sync with your network API contract. All right, but let's look at this in a little bit more detail still. So not only do you have to have this formal contract now, but these arguments that you used to pass into this method, these arguments now have to be serialized and then sent over the wire to be sent to some server. And that serialization requires a few things. First, it means that the data types that you're using here, they have to be serializable data types. So now what data types you can pass here is a severe subset of what was possible before. And you have to serialize these into some standard format that's actually part of your contract. And there's many serialization technologies out there, like Avro, Thrift, protocol buffers, Bond, and JSON, XML, or other examples of this. So serialization, it requires the allocation of memory, and it requires walking over the objects to serialize them. Sometimes the objects' data types themselves have to be defined as being serializable. This can be very expensive in terms of memory and time. Furthermore, the result also has to be serializable too. So the arguments you'll serialize on the client, you'll send them to the server where you will deserialize them. And remember, possibly in different programming languages. So I might serialize into JSON, and then on the server side, deserialize the JSON text that's coming into a .NET or Java object. And then on the server side, I'm going to send a result back. That'll have to be serialized into JSON or XML or something. And then the client is going to have to deserialize that into some result, which also has to be a serializable data type. So it's a restricted subset of types. And again, all this serialization and deserialization allocates a lot of memory, requires a lot of CPU utilization. In fact, we have seen certain customers where when they profile their service, the profiler is indicating that 90-some% of the time the service is spending in the serialization and deserialization code. So this serialization and deserialization can be a very expensive operation and can really hurt performance of your service quite dramatically, especially if you use serialization technologies that use things like reflection. Right? Reflection is done at runtime, which can hurt performance. Reflection is offered by things like .NET and Java. If you hand do your serialization instead, and you write specific code for it, then the performance could be greatly improved by doing that. Okay. But let's look at some other differences here. Let's compare and contrast an in-process method call to an out-of-process network request. Well, I've already been talking a good bit about the performance difference there. The network request is going to have much worse performance than the in-process method call. And you're going to be increasing network congestion, which now introduces a lot of unpredictability into the time it's going to take to make the call. So you have to be worried about unpredictable timing. A lot of times when people call a method and it's in the same process, they know that method's going to return, within, microseconds. But when you make a network request, that can be orders of magnitude longer easily. And in fact, the server may never reply at all. Maybe it has a bug in it, in which case you will just be hung. Network requests are unreliable. They're going to require retry operations now, right? You would almost never put a retry loop around this call to method here if it was in the same process, right? Or put that method call in a retry loop if it's in the same process. But if you make that a network request now, you almost definitely want to put this inside some kind of retry loop. Also, you might want to have some timeouts on it. There might be a place where if the server doesn't reply in, let's say, 1 second, you might just want to give up and move on. So now you want to introduce timeout into this infrastructure that you didn't have or think about before when it was a method call. There's also this thing called a circuit breaker, which is a very useful pattern to take advantage of. It's used typically to prevent denial of service attacks from your own clients. So imagine that your service is having a problem, and you have a lot of clients that are hitting that service. Well, those clients, they will retry to hit the server over and over and over again, but the server is really in trouble, and it's not going to all of a sudden start working. This circuit breaker pattern allows clients to try hitting a server so many times, and if within, let's say, 1 second there have been 5 failures, the clients just stop. And they say, look, I'm assuming failure on the server. I won't even try to hit the server anymore. This stops the server from being bombarded with a lot of network requests and having to deal with that, so effectively you are not causing a denial of service attack on your own service. And then circuit breakers, if they wait, let's say, a minute without making a request to the server because they've been assuming failure, they will then try again to make a request to the server in hopes that a minute has gone by and the server has fixed itself. But if the server fails again, they will immediately shut that down and then wait another minute before making other requests. But if the server comes back online, then the circuit breaker closes and allows traffic to go through. So I would highly encourage you to read more about circuit breakers. There's a lot on the internet about them. It's a very useful pattern. You should definitely be aware of it, and you should definitely be incorporating it into the client side of your services. Now, because the client side is going to retry, this requires that the server code has to be idempotent, because the server might get the same request multiple times, but you really only want to perform the operation once. So there has to be some additional logic on the server side in order to say, hey, I've already done this once, I don't need to do it again. This is idempotency. I'll talk more about it a little bit later on, but the way that you implement it is unfortunately domain specific. So I can't give you like a solid guideline, here's how to always do it. In some cases, it turns out to be very easy to do. In some cases, it turns out to be quite difficult to do. But as I said, I will talk about that more a little bit later on in this course. Well, because you're turning the method call into a network call, you're now going to have some security ramifications potentially. So the server could now be receiving requests from anybody, whereas before this method could only be called by code in the same process. So now you have a service sitting on your cluster, anybody could call it, so now you might want to introduce authentication to make sure it's being called only by entities that are allowed to call it. You might want to do some authorization there. You might want to encrypt traffic that goes over the wire, whereas you would probably never even think about encrypting these arguments or return values if it was just being passed around within the same process. This security is more typically required in a virtual network for compliance reasons. So sometimes, just to meet compliance reasons, you need to turn encryption on or authentication on. And sometimes if you're running third-party code that you may not trust within the same cluster, you may need to turn this on. And then the last thing I have here is related to diagnostics. You're going to have networking issues now, which you didn't have before. So what if something goes wrong with the network? You're going to have performance counters, event entries, logging that happens now, causality information, call stacks. The call stack now crosses over a network wire. The client makes a network call, and then the server continues execution. How do you track all of that? How do you know when something fails? What caused that whole flow to go from service to service? And if you're writing event logs with this diagnostic information, which is a really great thing to do, you should definitely be doing it. And then you should look at these logs later when failures occur. Be aware that on different servers, the clocks are not completely synchronized. First of all, within a cluster, all the clocks should be on UTC time. You want to use Universal Coordinated Time Zone for all the machines. But even when you do that, some machines are going to speed up, some might slow down. The clocks are not completely in sync. And so on one machine, the client, it might be 1 a.m. in the morning. You send a request and you log something there that you're sending a request to a server. The server might think it's 12:58 earlier, 2 minutes earlier. And then it's going to log that the incoming request came in. Well, if you try to look at those logs holistically, the server will effectively be reporting that the request came in 2 minutes before the client sent the request. So you have to be aware that this is a real thing that could happen, and you have to account for this, what we call clock skew, on these different servers when analyzing these log requests. So the point I'm trying to make with all of this is that it's not as simple as turning a method call into a network call. There's a lot of good reasons to do this, but it does introduce a lot of complexity. And what are the reasons to do this? Those reasons are the ones I spoke about earlier in this course, right? There are really 4 reasons to split a monolith into microservices: that scale independently, that different technology stacks, the 2 or more clients, and the conflicting dependencies. So you want to be really wanting to have 1 or more of these features in order to consider breaking things up so that a method call becomes a network call, right? That's the trade-offs. Okay? And hopefully that gives you a good sense of the networking and when to take advantage of it and the pain points that you'll have with it. In this section, I'm going to talk about that formal contract that you make for networking and how to version APIs that are related to that. So first thing I want to say is that API versioning is really just an illusion. You're not actually versioning APIs at all. And the reason is because you must always be backward compatible with previous versions. So what you're really doing instead is you're adding new APIs and you're stating that the latest version is the preferred one, right? This is the one you want the clients to ultimately migrate to because it's better in some way, right? It does more, it's better performance, for whatever the reason happens to be. The best way to go about doing this is that you put a version number on an API and you make this be required. And here I show 3 different example ways of accomplishing this. If you have a HTTP API, and let's say api.contoso.com, one way to put the version number in is to just put it as part of the URL itself, like version 1.0, and then whatever you want at the end, like products and users. Another way to go about it is the URL is the same, and then you have a query parameter, something like API version equal 1.0. And sometimes people use, instead of version numbers, they use some kind of date instead, like the year 2016, December 7th, and that ends up being their version number. So the important thing is that you think about this and that you choose one way of representing versions, whether it's dates or numbers, and that you integrate it into your API, and you really should do that from the get-go. That's the easier way to go, right? And it sets you up for a future of success. There is a sentence or a saying that nobody ever thinks about versioning until version 2. You're better off not being one of those people and think about versioning even from version 1. Assume that there will be a version 2 and think about it from the very get-go. When should you add a new API? You add a new API when you are changing some mandatory parameters to the API, when you want to change the payload format. There's a lot of people who used to use XML, but then they switched to JSON, for example, for the format. When you want to change the error codes, otherwise known as the fault contract of the API, and certainly if you want to change behavior of the API itself. Note, just as a point of an interesting side note here, that Azure considers a reply with a new JSON field as breaking. So in Azure services, for example, at Microsoft, if an API returns a new JSON field in the payload, that's considered a breaking change. On the other hand, though, Office 365 services at Microsoft, they don't consider that a breaking change. They say that if we just add another field to a JSON payload, that's okay, and that the clients just have to deal with that. Whatever you decide to do, just make it formal. Think about it up front. Have an understanding amongst you, your team, and your clients of the API so that you're all on the same page and you know exactly what to expect so that everybody can write code properly and appropriately to handle whatever may come up in the future. Let's talk a little bit more about defining network API contracts. So I say here define explicit, formal, cross-programming language, API, as well as data contracts that you're going to have between your clients and your servers. Contracts defined via code do not work, do not do this. Let me explain what I mean by this bullet. For a while there, certain people were going out and they were saying you can produce contracts with a contract-first approach, where let's say you sit down with XML or JSON and you go and define the contract. Or you can create the contract using what's sometimes referred to as a code-first approach, where you sit in your language of choice, and let's say you define some class or some interface, and the interface has methods in it, and the methods take arguments, and then there's some tool usually that can look at that interface and then go and produce the XML or JSON contract. From my experience, the code-first approach to making a contract does not work. It sounds nice. For software developers, it's really what you want to do because we like to think in code. But the contract tends to have weird things about it that takes an implicit dependency on your language of choice. Let me give you an example. The date-time class can be null in Java. In Java, they have a date-time class, and you can pass null. But in .NET, date-time is a value type, and so you can't pass null. So if I create an interface in, let's say, .NET, and I have a method that takes a date time as an argument, when that gets turned into a contract and then someone tries to call that or use that contract from Java code, they may try to pass in null for the date time, but it'll throw an exception when it gets to the server because that can't be deserialized. Right? Or if the server is in Java, then null is possible for date time, and the server may allow null to be passed and do something with that. But in C# or .NET code on the client, it's impossible to pass null for that. And so you must always pass a date time. Right? In addition, languages have other things like support for templates and generics and maybe nullable data types. And these kinds of concepts don't always work across language boundaries. So when you do code first, you're implicitly using these things, and you're not creating a contract by definition that can work across language boundaries. So I strongly discourage code-first approaches to contract. I strongly encourage formal contracts where you really think about the wire protocol and what is going to be sent across the wire, what that's going to look like, and make sure you come up with something that is easily amenable or work with lots of different programming languages out there. Now, there are starting to be some standard ways and open ways of doing this. So consider using openapis.org and Swagger.io. These are ways for you to create these contracts with some tools that are available. You can create them in XML or in YAML files, and then there's tooling available that can take these XML or YAML files and then can produce client libraries for lots of different programming languages. And these tools that allow you to define these contracts, they restrict you to the set of data types and features that are available across a large set of programming languages. So they help you produce these contracts in a way that's guaranteed to work across multiple programming languages. So I highly encourage the use of these for you. Then there's these tools available that create language-specific client libraries. But again, beware that what these client libraries do is they take a data type in your language of choice, they serialize it to some format, and then they send that across the wire. And then they take that information from the wire and they deserialize it. Again, the serialization and deserialization can have high resource consumption costs. It uses more RAM, it uses more CPU, and as I've said before, we've had some customers where 90% of their application code is being spent in this serialization, deserialization, other than doing real business logic work. So beware of that. There's many cross-language data transfer formats that are available. The kind of, default is JSON or XML, right? That's guaranteed to work because it really is just textual strings that you're moving around. There are some other more compressed binary protocols that are available, or data transfer formats that are available, like Avro, protocol buffers, flat buffers, Thrift, Bond, and really these things are a dime a dozen. There's like a new one popping up every month. So you can take a look at these. They always have pros and cons. Some are better in some scenarios than others. And really, think about what you're going to do here. And then you'll probably have to stick with whatever you come up with for, many years in the future. I mean, you could have a new versioned API, which is really adding a new API that has a new data format. You can do things like that. But again, the important thing is that you think this stuff through from the beginning. Another aspect of that is my last bullet here. Consider embedding a version number in the data structure itself, so that when you're reading something across the wire, the server can say, oh, look, somebody sent me a version 1 of this thing. I'll deserialize it this way. Oh, so the client sent me a version 7 of this thing. Well, then I will deserialize it this other way. Of course, the version number has to be kind of in a data transfer format agnostic way. Maybe it's the first couple bytes of the payload, or maybe it's in a header of an HTTP request, so that you can look at that and then you know what the payload is, so that you can deserialize it properly. Continuing our conversation of these explicit contracts and these client libraries, I want you to beware of leaky RPC-like abstractions. A lot of people really love these and they embrace them, but these also have some problems with them. So what am I talking about here? What I'm talking about is programmers like to have a simple life. I mean, we all do. And so to simplify programming, lots of different technologies are available that try to map method calls into network requests. In other words, it looks like you're making a method call, but in reality, this is a wrapper or a technology that is turning that method call into a network request underneath the covers. And examples of these, of which there are many, is RPC, RMI, Corba, Distributed COM, Windows Communication Foundation. I mean, just to name a few. But there's a ton of these, and there's like a new one every month on these things. In my experience, a lot of times these things do not work. And they do not, or they might work initially, but they don't work well in the long run. And the reason is because of, well, lots of reasons. So let's walk through some of those. The first is the network fallacies. You'll remember I started this section by talking about the 8 network fallacies. So because a lot of these APIs, they don't do retries for you. They don't support timeouts. They don't support circuit breakers. And these are things you really want when you're making network communication in this distributed cloud world. Also, you want to avoid chatty methods where you make lots of little requests to a server. Those introduce a lot of latency and they hurt performance a lot and they put a lot of congestion on the wire. It is better to have more chunky conversations between a client and a server, where the client says to the server, I want a big chunk of data. And then the server sends that chunk, then the client processes it for a while. Then it goes back to the server, says, I want a chunk of data, gets another chunk, processes it for a while. As opposed to, give me a piece of data, let me process it. Give me a piece of data, let me process it. That latter scenario is much worse. The chunky is much better. These RPC-like abstractions have issues about language-specific data type conversions. I already gave some examples about date times or nullable data types and generics. And here I mentioned also dates and times and durations of things. These are frequently different data types in different languages. They may not work the same way. Just whether null is allowed or not is different between languages. Versioning. When you create these wrapper technologies, these RPC technologies, which version of an API are they going to call internally? Version 1, the December 7th, 2016 version? You know, how do you know which version it's going to call? Maybe inside your program, at one place in your code, you want to call the version 1 of the API. Maybe at a different place in your program, you want to call the version 2 API. A lot of times these RPC abstraction things, they don't give you that kind of flexibility there. Authentication. How do you handle expiring tokens? A lot of times people are using things like OAuth today for the client to authenticate with the server. These tokens expire after a certain period of time, let's say 60 minutes. So how do you hand this token off to this RPC mechanism? How does the RPC mechanism refresh that token periodically before making a request out to a server? A lot of times that's not taken care of in the RPC mechanism. And then, of course, logging. If you send a lot of requests as query parameters, if you're doing HTTP for the communication protocol, if you send a lot of requests with query parameters or on the URL, a lot of times that URL gets logged on the server. But if you put some of the information in as headers, or you put some of the information in as the payload, a lot of times that information does not get logged into a log on the server, because the payload information tends to be too big and it would really pollute the log with a lot of extraneous stuff. So when you use these RPC mechanisms, you don't necessarily know what's coming in as a query parameter, what's coming in as part of the URL, what's coming in as a header, what's coming in as a payload, and how to deal with those things. You have less control over it. So, and then I mentioned again that the server's clocks are not absolutely synchronized with each other. That can cause skewing problems when you're looking at logs that are happening from clients and multiple servers. Now we've talked about these contracts and how to produce them, and a lot of times HTTP or direct HTTP requests is a better way to go than those RPC mechanisms. But let's talk about this retry that clients must do. Clients must retry failed network operations, and so you must have code in your client side in order to do this. The client code has to retry the operations due to the network fallacies, again, that we talked about earlier, timeout, topology changes. Also, you should avoid sticky sessions, by the way. Let me go into that for another moment. Sometimes clients make a request and they have a particular server that they're talking to, and then they would like future client requests to go to that same server. That sounds nice, but in this world where failure can happen at any time, we call that a sticky session, by the way. But in this world where failure can happen at any time, it's not a good model to have, because that server could go down at any time, and then the next client request that comes in might be sent to a completely different server. So when you're architecting your application, you really want to try to avoid using sticky sessions as part of your application, because they really just can't be guaranteed in a scenario where failure is inevitable. Clients must retry operations because of server throttling. If too many clients are making a request into a server, the server might report that it's busy, and then a client really should back off a little bit of time and then make a request again, right? You want to back off to give the server some time to catch up, to handle the requests that are coming into it, and then the client can make another request to have the server do some additional processing. You don't want to immediately retry if the service says it's unavailable or if it's returning an error. I mean, if it returns an actual error, then retrying should just regenerate the same error over and over again. There's no value in doing that. So this means you need to look exactly or specifically at the kinds of errors you're getting back from making a server request, and you have to intelligently retry some of them and intelligently not retry some of the other ones. Never assume that a dependent service is already up and running. Now, it's true in this world where we're going to have multiple instances running, you do your best to make sure that at least one instance is, or the orchestrator, it does its best to make sure that at least one instance is up and running. And so you can usually count on that dependent service is there. But there's also a chance that for some reason that service completely goes down. It would be good to be able to compensate for that in your code and not just keep hammering on service that just doesn't exist. You want to prevent distributed denial of service attacks against yourself. I've already talked about this earlier, and we discussed circuit breakers. I put a link here to a website where you can learn more about them, but it's a very popular pattern. You can find lots of information about it on the internet. Another thing that you want to consider using is exponential backoff, where your client makes a request to the server, for whatever reason, says no, and instead of just immediately retrying, you might wait a little bit and then go and try. If the server says no again, now you might want to wait longer before you retry again. And you have this exponential backoff that occurs up to some maximum amount of time before you go and try to hit the server again. This again just makes it so you're not just pounding on the server with a lot of requests and bombarding it. Now, for clients to do retry of operations, there is this assumption that the client is making, which is that the server handles these requests in an idempotent fashion. Let's talk about that. Services must implement their operations idempotently. An idempotent operation can be performed 2 or more times with no ill effect. That's the definition of what it means to be an idempotent operation. It can be performed multiple times with no ill effect. Now, some methods that take some input, do some processing, and return some output, they are just naturally idempotent. So I give an example here where, let's say I take a picture, an image, I upload it to some server, so the image is the input, the server does some processing, let's say it makes a thumbnail of the image, and the output is the thumbnail image itself. If I retry that operation and I send the same exact image up to the server, it will create the same thumbnail image and return the same output back to me. That is naturally idempotent. I can send the same image multiple times to the server. It does the same exact processing, sends me the same exact output every single time, and no ill effect is happening on the server. So that's, again, naturally idempotent. Another example would be a calculator app. The client sends 2 plus 3 up to the server returns back 5. If the client sends 2 plus 3, the server sends back 5 again. It is just naturally idempotent operation. But methods that have side effects are not naturally idempotent. And these require that you, as the developer of the server, do some additional work to guarantee the idempotency. An example of an operation that is not naturally idempotent would be repeatedly adding $100 to a specific bank account. So if a bank account has $0 in it, and then I send an operation to add $100 to the account, the server is going to add $100. But if I get, let's say, a timeout because I'm waiting for the server to reply, but it seems to be taking too long, my client might retry that operation and tell the server to add $100 again. If the server just does that blindly, it's now going to add another $100 to the account, and it has $200 in it. That causes state corruption, and we don't want that to happen. So the server has to do something in order to guarantee idempotency here and make sure that this adding $100 is idempotent and has no ill effect. And I'll talk more about what it can do on the next slide. So I wanted to put here in bold letters at the bottom. What we want is exactly once semantics. We want the client to send a message to the server and for that message to be received and processed exactly once. But in this world of failure, the way that we get exactly once semantics is that the client does retries and the server makes the operation idempotent. Right? And that's how we implement the exactly once semantics. Client does retries, server makes the operation idempotent, and that's how we get exactly once semantics in a world where failure is inevitable at any time. Let's talk about idempotent CRUD operations now. CRUD stands for create, read, update, and delete, and these are the four most common operations that are done to any kind of piece of data that you have. Right, like a bank account. I can create a bank account, I can read the balance of the bank account, I can update the bank account, I can delete the bank account. Okay, so for the create, what you're effectively trying to do is you're trying to call a create method. The way that you'll typically do that is by performing an HTTP post operation against a server. And then the create operation goes and returns an ID. The post verb of HTTP is not defined to be idempotent. That is, HTTP, the specification, says there are certain verbs that you, the implementer of these HTTP operations, you must make them be idempotent. The HTTP spec says that post itself does not have to be idempotent, but you might want to make it idempotent anyway. And there is a pattern that you could use to do that, which I will talk about at the bottom of this slide. So let's just postpone that for a moment and I'll get back to it. Let's look at a read operation. A read operation is where the client performs a read against some ID. Right? This might be the bank account number, for example, and then it's going to go and get some data back. Typically, we do this with an HTTP request using a verb of get, head, options, or trace. Now these verbs are naturally idempotent. If I say to a bank account how much money is in you and it returns me the number, if I say again how much money is in you because I retry, it should return the same number. So it's naturally idempotent. Usually there's nothing special you have to do here for a read operation. Let's look at an update operation. To do an update, the client performs an update operation, maybe against the ID, like a bank account, and then the data of what you want the operation to become. So here, we're not saying add $100. Here, we're saying more like, I want to update the bank account so that it has this amount of money in it. Right? So not add to what's already there, but make the balance be this value. This is usually done with an HTTP verb request. Now, usually for HTTP verbs, or a put verb rather, it's last writer wins. So if multiple clients are doing puts, or if you do a retry, do a put in a retry loop, you're ending up putting the same piece of data there multiple times. And so in effect, it's idempotent. You're saying, I want the balance to be 100, I want the balance to be 100, I want the balance to be 100. If you do that in a retry loop multiple times, the end result of all those is the balance is 100. And then delete. Well, you can say delete with an ID. Usually we do that with an HTTP verb of delete. Now the first time you call this, it's going to delete the ID. If you put this in a retry loop and you try it again, then the server is usually going to reply with, that thing doesn't exist, because you deleted it the first time, so now it doesn't exist. So the way to make this okay on the client side is if you execute a delete operation and the server says it's already gone, then don't treat that as an error. Treat that as, okay, then great, I did the delete. Even though the delete was done earlier, you just treat it as I did the delete, and then you just move on as if everything is okay. So HTTP, as I said, the specification, it requires that most verbs be implemented in an idempotent way. But post is not one of those verbs, and post is frequently used for create operations. So instead, you can take something that's not idempotent and make it become idempotent using what I refer to here as this idempotency pattern. Let me walk through that pattern with you. So first, the client is going to ask the server to create a unique ID. So it makes a request to a server and says, server, give me a unique ID. This could be a GUID or just some value that's meaningful to the server. It just has to be unique is the important part. Now, you could put this in a retry loop, and if you do, then the server is going to return new unique IDs each time. But the last one is the one you care about. The earlier IDs that you got back, you can just throw those away. If the client is a trusted client, then the client can create the ID themselves. So in other words, if you have clients that are talking to a server, but the server knows that the clients are going to create unique IDs, right? Because maybe they're creating new GUIDs, right? Somehow the server can trust that the client or clients are creating unique IDs, then you could avoid a network hop by having the clients just create the IDs rather than going to the server to construct an ID. Now, once we have a unique ID, step number 2 is that the client is going to send the ID up to the server with the desired operation, like add $100 to a bank account, right? Somehow that information is encapsulated in the payload and sent up to the server. And this operation can, of course, be retried. Just like creating the ID could be retried too. Now, what the server is going to do when it receives this request is it's going to look up the unique ID in some kind of log. And if the ID is not in the log, then the server will perform the operation. So it says, okay, I've been told I'm supposed to add $100 to this bank account, and here's the unique ID that identifies this operation I'm supposed to perform. Let me look in this log and see if I've ever performed this ID operation before. And if it hasn't, it says fine, then I will perform it, and it will add $100 to the bank account. Then it will go and log the ID. So if another request comes in for the same ID, it was done, and so it just won't do it again. And in either case, the server will return OK, saying I did it or I did it earlier. It's still an OK operation to kind of indicate that it was done. You'll notice I have a note here on the right that says must be transacted. This is very important to understand. Looking up the ID in the log, doing the operation, and logging the ID, that has to be done as an atomic ACID transaction. If it is not done that way, then you could look up the ID in the log and start doing the operation. While you're doing it, and before you've logged the ID, the client could retry. You look it up in the log and it's not there yet. And therefore, you do the operation twice. That's not what you want. Now you've broken the idempotency of this operation. So you cannot do it that way. These 3 things have to be done in a transacted way. And then you might say, well, if it's not in the log, let me go log it first, and then I'll do the operation. That also doesn't work because it's not in the log, you log it, and then you crash. So now you never did the operation. But you think you did because you logged it. So if the client retries, now you'll say, well, it's in the log, and so I did it, but really you didn't do it. So these 3 things have to be done as a transacted atomic unit, and that's very important that you do that. Now these logs of these IDs will grow without bounds over time, and that's not ideal either. So my last bullet here is, on the server side, you want to periodically delete old logs to avoid this unbounded growth. Otherwise, you're paying for the storage of these logs and maintenance of these logs, and you want to try to keep them as small as possible. So that's basically the pattern for how you can make a non-idempotent operation become idempotent.